Hello! In this video, I'd like to talk about a game that we played at Mathcamp called Axiom or Theorem. This game is based on a sillier game we played called Color or Country. In Color or Country, players would take turns naming either colors or countries. If they named a country, they lost, and if they named a color, the game would continue. We had lots of fun at Mathcamp exploring the possibility space of games, and a lot of our games, like Color or Country or Rock, Scissors, we deliberately designed to have no strategic content. There's something really interesting to be said about games from the fact that us math campers, despite also enjoying very strategic games, enjoyed these absurd games as well. Part of it was that we enjoyed making up silly games and just being silly in general, but games also provide people with structured opportunities for social interaction, regardless of their strategic content. Now I can talk about Axiom or Theorem. In Axiom or Theorem, players take turns building up an axiom system. If they name a new axiom, the game continues, and if they name a theorem, something that can be proved from the previous axioms, they lose. Now, when I say an axiom system, you should be thinking of the sort of axiom systems for various classes of structures. The sorts of axiom systems we were being introduced to at Mathcamp. For instance, the axioms of a group or a ring or a field, the axioms of a linear ordering, or the axioms of ZFC set theory. Specifically, the game worked as follows. Players would, in advance, agree on what kind of structure they wanted to talk about. What were the operations, relations, and constant symbols of the structure? How many inputs did the operations and relations take? For instance, would we have a binary operation like addition or multiplication, or maybe a unary operation like a group's inverse? Or would we just have relations, maybe a binary relation like a graph, a linear ordering, or a model of set theory? In model theory, a set of operations, relations, and constant symbols and their associated arities is called the signature of a structure. Once players have agreed on a signature, they take turns making first-order statements in that language. Statements built up out of variables, the operations, the relations, and the constant symbols. Equality. Equality comes for free in model theory. It's very often the case that you don't even need to specify. Of course, we can say that two things are equal to each other. And we also have Boolean operations, and or not implies, and quantifiers for all and there exists. And specifically quantifiers restricted to our structure, right? So for all x in our structure, or there exists an x in our structure. On a player's turn, there's three possibilities. First, their statement could be provable from the previous statements. That is, every structure satisfying the previous statements necessarily had to satisfy the statement just played. In this case, we say that the player has played a theorem, and so they lose. Second, their statement could be disprovable from the previous statements. That is, no structure satisfying the previous statements satisfies the statement just played. If I remember correctly, the convention was to just laugh at the player and let them go again. Or third, the player's statement could be neither provable nor disprovable. That is, some structures satisfying the previous statements satisfy the statement just played, and some don't. In this case, the player has played a new axiom, and the game continues with this new axiom system. We found it really necessary to fix the signature at the beginning of the game. In early playtests, players would regularly introduce new notation, new operations, new relations, or constant symbols. This made things a bit too easy. Since nothing had been established about the new notation yet, it was much easier to come up with statements that said something new. But I wouldn't call these new axioms so much as new definitions. This led us down a whole rabbit hole trying to characterize the difference between an axiom and a definition, and how to incorporate them into the game in a way that was fun, but ultimately I don't think anything came of that. So let's go through an example game. For this game, the players have agreed on a total binary operation using addition notation and a constant symbol b. Player 1 plays associativity. For all x, y, and z, x plus y plus z is equal to x plus y plus z. This has the effect of keeping the game in really familiar ground. We already know that we're working in a semigroup, and we can use notation like x plus y plus z without worrying about ambiguity. If you're trying to work in non-associative structures, you wind up having formulas that just have tons of parentheses in them, and you have to make sure that all the parentheses match up correctly. It's really annoying. Player 2 plays a right inverse-like play. For all x, there exists a y such that x plus y equals b. Of course, this isn't quite an inverse yet because we don't know that b is the identity element, but if it were, then this would be a right inverse. But player 1 decides to mix things up and plays for all x, x plus b is not equal to x. So b is kind of the opposite of an identity. One of the useful strategies in this game is to try to think of various structures that satisfy the axioms so far. For instance, the integers with addition and b assigned to any number other than 0. Player 2 gets too silly and plays for all x not equal to b, b plus x equals x. The idea here is that b should be a left identity but not a right identity somehow. Unfortunately, this contradicts the previous axioms, and I'll let you try to figure out why. But that's okay. If a player plays a contradiction, we just laugh it off and let them try again. Frustrated, player 2 decides to play there are at most 3 elements. There exists x, y, and z, such that for all w, w equals 1 of x, y, or z. Again, it's important to remember these quantifiers, they refer only to elements in the structure, right? So there exists x, y, and z in the structure such that for any w in the structure, w is 1 of x, y, or z. At this point, we don't have to worry about large or infinite models that are hard to reason about. We can do a brute force search and find that there are only 5 structures up to isomorphism that satisfy all these properties. At this point, if a player says a statement that's true of all 5 of these structures, then it must follow from the axioms, right? These are the only 5 structures that satisfy the axioms, so anything that's true of all of these structures follows from the axioms. And so is a theorem. If a player says a statement that's false of all 5 structures, then it contradicts the axioms, and so the player gets laughed at. At this point, a player has to play a statement that's true of some of these structures and false of others. So player 1 plays, there exists an x such that for all y and z, y plus z is not equal to x. That is, there's some x that's not in the range of the addition operation. This is true only of these 2 structures. In the first, that x is 2, and in the second, that x is 1. So now there are only 2 structures that satisfy all of our axioms. Player 2 plays, for all x, if x is not equal to b, then x plus b equals b, which is only true of the first structure. At this point, player 1 cannot move. Any statement they make is either going to be true of all of the remaining structures, and so a theorem, or false of all the remaining structures, and so a contradiction. And so the game is over, and we say player 1 has lost. Of course, in this example, neither player is playing optimally, but that's not really the goal of Axiom or Theorem. The goal of Axiom or Theorem is to have fun creating a brand new branch of mathematics that no one has ever even bothered looking at before, and get stumped over really basic questions, like, does this new type of structure necessarily satisfy this kind of property here? Just like how our food tongue game was a miniature exploration of how pigeons develop and evolve, Axiom or Theorem was a miniature exploration of developing axiom systems. By creating completely arbitrary axiom systems for ourselves, it helped us see the arbitrariness in the axioms of piano arithmetic, or ZFC. These axiom systems are trying to capture a specific concept, so they're definitely not fully arbitrary, like the ones that you get from Axiom or Theorem. But we have other axiom systems for the natural numbers or for sets, and it's mainly an accident of history that these two became the primary ones. It also helped us see the arbitrariness of what sorts of structures we wind up studying. In an alternate history, mathematicians learn about monoids, or semigroups, in their abstract algebra class, with maybe a side mention of groups as monoids with inverses. Axiom or theorem is also a great way to learn about some concepts in model theory. We say that an axiom system is complete if any statement can be proved or disproved from it. That is, nothing can be added to it in the game. If we reach a complete axiom system, the game is over. The axioms we came up with in our example game are complete. Of course, we want our axiom systems to be consistent, that is, unable to prove a contradiction, which the game ensures by not allowing players to add axioms that contradict previous axioms. Of course, some axiom systems, like piano arithmetic or ZFC, we can't prove to be consistent. One goal of this game that we try to, but don't really achieve, is having an independent axiom system. Ideally, in an axiom system, no axiom can be proved from the rest, although we might want a redundancy if it improves ease of use, if it makes it easier to prove things from our axiom system. Our condition that any new axiom we add not be provable from the previous axioms is good, but new axioms might allow us to prove old axioms. In the axiom system we got from our example game, axiom 2 actually follows from all the others, so this axiom system isn't independent. We can remove axiom 2 without changing its consequences. This game also gets us thinking about finite versus infinite axiom systems. Our game came to a sudden halt, but this isn't necessary. There are plenty of axiom systems out there that are infinite and necessarily infinite. And finally, a lesson about model theory that I've subtly included throughout this video is the completeness principle, that we can reason about proofs in terms of the properties of various structures. So the following are equivalent. Some formula A can be proved from some formula B, and here I'm using proof in the sense of a formal sequence of steps following one after the other, according to the rules of any one of a number of common proof systems. And any structure satisfying B satisfies A. All B's are A. This isn't a trivial result, and it's one of the key results in model theory, that we can reason about structures by reasoning about proofs, or reason about proofs by reasoning about structures. So, thanks for watching. I hope you'll go out and play some games of Axiom or Theorem on your own. Also, feel free to leave a comment if you have any questions, or just let me know what you learned from this video. And, as always, be kind to each other.